So, good morning, everyone. Today we have in the first session Alexander Ihler. He's an associate professor at UC Irvine, and he does quite a lot of research in AI and machine learning, and especially in approximate inference for graphical models with applications to things like machine learning and data mining. So today he'll be talking to us quite a bit about that specific topic, approximate inference, so please welcome him.
Thanks. I'll apologize for two things right off. One is that I have a cough, so hopefully that won't get in the way. And the other is that my slides are a little bit cluttered. So I teach, I give two kinds of talk, one of them for seminars and conferences that are very clean and so on. And then for my class, I tend to have, I tend to find that the students have a lot of trouble getting the details of the actual implementation if I do that. So instead, these slides are from my class, and so they have a lot of possibly over-detailed examples, but with actual numbers. So if you are interested in following up on them, you can actually go in and verify that you understand what's happening in the example. I'm also a very informal speaker, so feel free to just wave and get my attention if you have any questions. So we've already seen a couple of talks at MLSS on graphical models. Graphical models are a popular formalism for describing large, complex systems over many variables that are made up of smaller, simpler interactions. So you have a complex system, but the system itself is described by only relatively small and compact interactions. So the typical way that we'll describe this is using a product formulation. So you have some function f of x that's a product of non-negative factors, f alpha, where alpha is an index of a subset of the variables. So x alpha is some small set of variables, and f alpha describes the interaction between those variables. It'll also be useful often to talk about the logarithmic form of this. So I'll sometimes talk about f, where I mean a product of smaller functions. And sometimes I'll talk about theta, where I mean a sum of smaller functions. So you can just think of theta as being the logarithm of f. So each of these is a useful way of looking at things at different points. Common examples of these are things like Bayesian networks, where the factors f alpha are conditional probability distributions. So each term is a conditional probability for one of the variables given a small subset of other variables. Or factor graphs where you have correlative factors that instead of having a conditional probability semantics, just have a compatibility or a correlation. A few examples of these from different settings. I think Justin actually used several of these examples in his talk on graphical models also, so we apparently think the same way. One example are things like protein sidechain prediction problems or protein folding problems. So here you want to represent the shape that a protein takes on. And so the variables are actually the positions of the side chains. So the protein is made up of a sequence of amino acids, and the amino acids have this tail that sticks out, and the tail can go in various positions in the three-dimensional space, and they tend to end up in a relatively small number of positions. So you can discretize those based on your experience with other proteins, and the positions that you take on and discretize, those are called rotamers. And then you can describe how those things interact. So if you have a couple of neighboring amino acids, they might be sticking out in 3D space close to one another, and they have some energy of interaction. And so the task is to figure out what rotameric positions of all these things go together to find the minimum energy configuration. So in that case, what we want to do is find the most likely configuration of the system. So the MAP, or most probable state, X star, so the setting of the entire system that maximizes its probability, or possibly just the value of that, so the actual energy. So this is a combinatorial optimization problem. So we'll always think of X as being discrete, and we want to then optimize over this discrete space. Another example are things like conditional random fields for computer vision and image recognition. So here the variables are the labels of each pixel. So we have some image that we observe like this, and what we want to do is predict what object is at each pixel in the image. And so we have factors that show how the image appearance relates to what class we think it is, and how neighboring pixels are smooth and related to one another. And so the typical task here is that we want to do some kind of learning from data. So we have labeled data that look like this, and what we want to do is learn a model, and typically that involves likelihood calculations. So we might want to do summation or marginalization tasks so that we can optimize the likelihood of our model. So these are things like computing the marginal probability of each variable. So that's summing over all the variables except one. So this is calculating the net effect of the model on each individual variable. Or the sum over all the variables is called the partition function, and that's the constant that normalizes the distribution. So this is key for calculating the probability of your data. And even more generally, you can look at graphical models for looking at decision-making problems. So influence diagrams are a generalization of Bayesian networks that include not just random variables, but also some decision variables that encode a policy, and utility nodes that tell you how much you like a particular set of outcomes. And so then you can describe a potentially multi-agent decision problem using a graphical model. And so in that case, what you want to do is come up with a even more general inference task. So here I'll be a little bit glib and just call it marginal MAP, which is a simple task where you're maximizing over some subset of the variables while marginalizing over the rest of the variables. More generally, in a decision-making system, this is the maximum expected utility problem. But so here, we not only want to marginalize over some of the variables, like the random variables that are not of interest, but also maximize over other variables that represent the policy, for example. So this is a generalization of both the previous tasks. So if we didn't have any maximization variables, XM, we'd have a standard summation problem. If we didn't have any summation variables, we'd have a combinatorial optimization problem. Okay. So these are the types of queries that we're interested in answering about our graphical models. And all of these are, in general, NP-hard. So in some special cases, they're efficient, but most of the time, they're not. And in general, these get harder as we go down this list. So the combinatorial optimization is NP-hard. The summation inference is sharp P, and mixed inference is NP to the PP, or something like that. So in general, in all of these, we're going to be unable to guarantee that we'll get efficient, correct answers. So we're going to focus on approximation algorithms. So there are lots of different frameworks for thinking about approximate inference, and I'm only going to talk about a small part of them today. But I just thought I'd give a very quick overview of perhaps the two paradigms that one might think about, which you'll see in other talks and probably have already seen in some of the talks. So one framework that you might think about, I'll call configuration or tuple-based, where we reason about a complete configuration of the entire system. So these are things like search. So we might have a search tree. So here we have a level of nodes for each variable, and the leaf nodes correspond to all of the exponentially many configurations of the system. And we can think about optimizing, finding the most likely configuration of the whole thing using a standard search algorithm like A** or depth-first search or something like that. And so we're explicitly reasoning about these complete configurations of the system. Similarly, Monte Carlo methods can be thought of in this framework. So things like, say, importance sampling is a random exploration of this search tree. So we draw a configuration of the system X1 from some proposal Q. Then we draw some other configuration X2 from the same proposal. And rather than enumerating this exponential space in the search tree, we explore it stochastically. Markov chain Monte Carlo works kind of the same way, right? We have a configuration of the entire system, and then that configuration changes as we do our Monte Carlo samples. So we update small parts of that system to switch configuration. So we might start with some initial complete vector and then perturb it in random ways so that we'll end up exploring this space and approaching whatever our desired target distribution is. Okay, so this is this kind of framework ends up thinking about reasoning about entire states of the system simultaneously. In contrast, what I'm actually going to spend my time on today are what I'll call clique or table-based reasoning, where rather than reasoning about a setting of the entire system, we're going to reason about small groups of variables in the system, so subsets of variables in the system. And these are things like variable elimination for exact inference. As you eliminate the variables, you end up with tables over collections of other variables. And in particular, what I'll spend most of my time on, which are variational approximations. So things like mean field, belief propagation, and its variance. And the nice thing, one nice thing about this sort of clique-based reasoning is that it often leads to very simple message passing algorithms. So these tend to be very distributable, since you can partition up the cliques that you're going to reason about, and then these cliques just share information between themselves, leading to message passing optimization algorithms. Okay, so I'll just start with a few quick preliminaries on notation and frameworks. Then I'll talk about some approaches to maximization. In fact, these are actually the same approach, but from different perspectives. I think it's revealing to see how they all connect to each other. Probably about then, we'll all want to take a break and get some coffee. And then afterwards, I'll talk about the same kinds of ideas, but applied to summation problems, and eventually a little bit to mixed inference problems as well. Okay, questions before I like to pause and. It's familiar to everyone, I hope. Okay, so one of the key tools that we're going to use for variational inference and reasoning is an idea called reparameterization. So reparameterization is an operation which changes the factors of our model, but leaves the actual model unchanged. So let me see if I have a. Yeah. So we have our model f of x, which is a product of some factors over small cliques. And we're going to change those factors in such a way that the product of factors stays the same, but changes the parameters of the individual factors. So you can think of a small pairwise system over 3 variables, x1, x2, x3. So here we have factors. These factors are over, say, x1 and x3. And what we can do is redefine new factors, say f tilde, and just change them in a way that leaves the product unchanged. So perhaps I'll multiply the factor over 1, 2 by some new function, g, some arbitrary function, g of x1. And then I'll just divide away g in a different factor. So I have 2 factors over x1. One of them I'll multiply by g, and another one I'll divide by g. And so now the product is unchanged. So here, for example, I might take this table and multiply it by a factor over x1 to get a new factor. So the second row has been multiplied by 2. And then I'll just take another table and divide by the same factor, so that now the overall product of functions over here is exactly the same. Okay? So this gets used by variational reasoning. We're going to use this reparameterization trick to try to expose useful things about the distribution into these original factors. So, for example, I'll talk about dual decomposition, which got talked about yesterday as well. And that tries to expose the maxima of the distribution in these individual factors using this reparameterization trick. Okay. Another useful framework to think about things is to think of these factors as being a model in the exponential family, and to think about our model in a vector space. So again, usually what we'll think about is that we have a product, or in this case, a sum of functions, theta, right, which we can think about as tables defined over these discrete variables. But it's often useful to think about this model as being a point in some high-dimensional space. And so we'll think about that by describing the model by a parameter vector using the exponential family form. So effectively, this just vectorizes the parameters of these log factors. So we can make a vector theta that's constructed just by collecting all of these factors together and stringing them out into one long feature vector. So here we're enumerating all of the parameters that go with our function over x1, our function over x2, our function over x1 and x2 jointly, and so on. And so this vector now describes the model in an invertible way. And this is actually an exponential family form in that exponential family distributions have a natural parameter theta and some features u. So this describes an overcomplete exponential family form. So our features u, we can take any assignment x and come up with a feature vector whose dot product with theta will be exactly equal to our model evaluation. So for instance, if I have some state of this system, 0, 1, 0, right, to evaluate the model, I would look up theta 1 of 0, theta 2 of 1, theta 3 of 0, theta 1, 2 of 0, 1, and so on. And we can create a parameter vector here, theta, and our feature vector u, where we have entries of this feature vector corresponding to each variable's state. Right? So in this part of our feature vector corresponded to our factor theta 1. And we can create a feature. So if x1 equals 0, we make this entry 1. Right? If x2 equals 1, then we make x2's 1 entry 1, and so on. And so now the dot product between our vectorized model theta and our feature vector u will just extract out exactly the same value of the function that we had before. Okay, so this is just a transform to go from writing these table-based representations to this vector form with some feature vector u. Okay. All right, so now let's look at this and see how to do combinatorial maximization in this setting. Okay. And so again, I'm going to talk about this taking on 3 different perspectives of the same approximation, in fact, because I think these perspectives show different things and will shed some light on how things fit together. Okay, so So we're interested in maximization first. So we have some model, which is a product over smaller factors. We want to find the optimum of this function. So we want to find the maximum over all the configurations of the system. And if we have a tree-structured model like this, this turns out to be very easy, and we can do it using variable elimination or dynamic programming. Okay? So if we have a tree-structured model, then we can always select one of the variables, some leaf variable like x1, to eliminate first. We collect together all the variables that involve x1 and all the factors that involve x1 and eliminate x1 from them. So here's a factor over 1 and 4. And when we maximize over x1, we get a new function that's only over x4. And you can think of this as a message being passed in this tree-structured graph. So, so having eliminated x1, we now get a new system that's over a smaller number of variables. We can choose another variable to eliminate, like x2. Again, selecting a leaf, we collect together all the factors that involve x2. Eliminate that, and get a new factor over only x5. And as we proceed, right, we can collect together, so for example here, when we want to eliminate over x4, we collect together all the factors that involve x4. So here we have two singleton factors stemming from our previous eliminations and one pairwise factor, f4, 5. And eventually we end up with an elimination over all the variables. And for trees, this turns out to be very efficient. There's always an ordering which going from leaves to root, which doesn't create any larger factors than we originally had. So in this case, I had only pairwise factors, and by working from leaves to root, I only ever had to deal with factors over pairs of variables, right? So, so I never create any larger factors. So for trees, the computational complexity of computing this optimization problem is the same as specifying the original model. Unfortunately, in more general graphs with cycles, this starts to break down. So we can still do the same procedure to try to optimize. But now, when we go to eliminate over some variable x1, we collect together all the variables that involve x1. And now, this function will be a new function over all of the neighbors of x1 in our graph, right? So here we compute a function over x1, 2, 3, and 4 jointly. Maximizing over x1 gives us a new function over 2, 3, and 4. Okay? Note that this graph actually wasn't all that complicated. I intentionally selected a bad elimination ordering so we would get a large function here. But in general, this happens. But we can still proceed using this variable elimination form. We get a new function over 2, 3, and 4. We can choose another variable to eliminate, like x2, collect together all the functions, and so on. Okay? So in general, the cost of doing this procedure will be the size of the largest table that we end up creating, or the size of the largest table that we created as an intermediary. And since these are discrete variables, the size of that table will be exponential in the number of variables that are being reasoned about simultaneously. So here we're reasoning about 1, 2, 3, and 4 jointly. So if they all take on, say, d values, then that's d to the 4th. We're creating a table with size d to the 4, and then eliminating to get one of size d to the 3. So this procedure is computationally exponential in the size of this scope. The scope created is usually called the induced width of the ordering. The minimum over all possible orderings is then called the tree width. So the tree width is a fundamental concept that limits how efficient we can be doing exact inference in a graph with cycles. Okay? Yes.
So why was it elimination?
What I should have done is eliminate x3 first. So that would only induce a function over 3 variables and create a new function over 2. And so I could have done it for only cost d cubed instead of d to the 4th. But I intentionally picked x1 instead, which is not a smart thing. Other questions? Okay, so so very rapidly with real problems, the exponential size of these intermediate functions becomes prohibitive, and we aren't able to store it in memory or deal with the time aspect as well. So we need some way of approximating the process. And a classic method of approximating this variable elimination form is called mini bucket. So this is from actually 96 or so, but the reference I gave is from 2003. And this just approximates the variable elimination process. So this is our sort of first perspective on how to do approximate inference in the system. So the idea behind mini bucket is to still do this variable elimination procedure, but to replace any elimination that's too expensive with something cheaper. So here, for example, I'm supposed to eliminate over x1, creating a function over 2, 3, and 4. But I've decided that that function is too large for me to create. So instead, I'm actually going to think about partitioning this group of factors up and then eliminating within them separately. So one way of thinking about this is to think about so this factor over 1 and 2, 1 and 3, and 1 and 4 all involve x1. But if I group them and eliminate over x1 separately in this pairing and in this factor, you can think of that in some sense as splitting the x1 in these factors so that I have one variable within this pair and then a separate variable in the other set. And it's easy to see that if I were to maximize over x1 jointly in this system, it would be a smaller value than if I maximize over them separately in the two values, right? So the maximizing value of x1 for this pair and this factor might be different, and so this the product of the two maxes will be larger. Okay? So then you just proceed doing exactly the same thing that you did in variable elimination. So this now creates a new factor over 2 and 3. This creates a new factor over x4, and then you just keep processing in sequence. And so this is a classic idea that is typically used for creating search heuristics and doing approximate elimination. So a nice thing here is that the computational cost is controlled by the user. You can select exactly how many of these, how large these factors you're willing to deal with are. This is usually called the I-bound. And so if you're willing to use larger factors, you tend to be more accurate, but more costly. There's also a degree of freedom. So I mentioned this reparameterization process. So there's a degree of freedom here, which is that once I'm treating this product of factors separately in two different mini buckets, I have the freedom to change how those factors are represented using this reparameterization trick. So in this bucket, I might multiply by some arbitrary factor r, and then divide by that factor in this bucket. Depending on what factor r I choose, I'll actually get different results. So the question in a system like this is, how should we set this reparameterization function r? And so to see that, I think a different perspective will be helpful. So we're going to switch to a slightly different view. This is a nice procedural approximate variable elimination form. But to sort of understand how reparameterization affects the results, I think the integer linear program form and dual decomposition view is a very helpful one. Yeah?
You also have another degree of freedom in choosing the tags split up, like split F1.
Yes, you do.
One F4 into one bucket.
Yes, that's exactly right. Yeah, you have the partitioning choice and the reparameterization choice. Yeah. Other questions? Okay, so I'm going to switch direction for a second, and this will connect to this mini bucket view in just a minute. So let's back up and start with a different view of combinatorial optimization in this graphical model, which is the integer linear programming version of optimization. So again, we're doing map inference. We want to find the optimal configuration of our system, where our system is made up of a product of functions. And for notation here, I'm actually just going to use pairwise functions, because otherwise it just becomes notationally very heavy. So we'll just assume that all of these factors are either over single variables I or pairs of variables I and j. Okay? And again, we can write this, this model using this overcomplete exponential family form. So we'll take the log of all these factors. So we now have a bunch of log factors theta, which when added together define log f. And we can take those factors and vectorize them so they become one long vector of all the values in them. And we have this feature vector u that describes our configurations x. So again, each of these tables has some set of entries in u. And so I'll use notation u1k of x to mean the indicator of whether x1 takes on value k. So here I have x1 takes on value 0, so u1, 0 is 1, and x1 doesn't take on value 1, so u1, 1 is 0. We'll also have notation for pairs, so u1, 2 are the indicators associated with the pair x1, x2, and it'll be 1 if they take on value kl. So here, for instance, x12 took on value 0, 1. So out of this 4 possibilities for x12, one of them is on. Okay. So then optimization over x can just be viewed as this integer linear program over this vector u. Right? So what we want to do is find the vector u that maximizes its dot product with theta, subject to the fact that u has to correspond to some configuration of x. Okay? So if we think about what the conditions that define a configuration are, we need for every variable I to take on, this u vector is binary, right? uik is either 0 or 1. We need for every variable xi to take on exactly one value k. So if we sum over all the values of k, and they're binary, we should find that exactly one of them is on. Same thing for pairs. So if we look at each pair ij, that pair ij should take on some configuration. And so if we sum over all the configurations, we should find exactly one of them is on. And then finally, our indicator variables on pairs, ij, should be consistent with the singleton variables. So if we look at this, at say uij, if its entry, so if xi takes on value k, then one of the entries of ij kl should be on. So this is really just a linear way of writing this condition that if uij kl is 1, then uik and ujl should both be 1. So this is just framing that if our indicator vector u tells us that xi and xj take on some value, then the other part of the indicator vector u, corresponding to xi by itself and xj by itself, should tell us the same values. Right? So this is just the conditions of encoding some configuration x into this binarized vector. Okay, so so then this is an exactly equivalent way of optimizing it, and it's an integer linear program. We have a linear objective, a bunch of linear constraints, and then some integrality constraints. Right? So if we want to approximate this, right, integer linear programs are hard, but we can relax them to regular linear programs just by relaxing this integrality constraint. So we change notation from u, the binary vector, to mu, some real number between 0 and 1, and just have the same set of linear constraints, the same linear objective. And now, since we've relaxed this problem, we're no longer restricted to taking on binary values, the objective function must be larger than the true optimum, right? Because we have a constrained optimization and we've relaxed some of those constraints. Okay, so this is the linear programming relaxation of MAP. This is not terribly useful. I don't know anybody who actually solved the LP form of these things, but lots of people solve the dual of this. So the dual is something called dual decomposition. So we can take our original graphical model, described by maximizing over the collection of factors together, and create an upper bound of it that's given by just maximizing over each factor individually. So here we're computing the MAP of the entire system, so we need a joint configuration X that optimizes the entire thing jointly. And our relaxation of that will be to just individually maximize each one of these functions. So since each function can take on a configuration that's inconsistent with the other functions, this is an upper bound on our true optimum. So this is a very straightforward bound to see. And it's exact if all of the configurations actually agree with one another. So if the configuration that the pair 1, 2 takes on agrees with the configuration that the pair 2, 3 and the pair 1, 3 take on, then that means that there is some joint configuration that matches exactly this value. Okay? So we can take this relaxation and try to tighten it by just adding reparameterization properties. So we'll just, each of these individual problems, each of these individual factors, we'll add an extra term, lambda, that cancels with other terms. So here, for example, I'm going to add a function lambda 1 to 1, 3 of x1, and another one over x1 here. And I'm going to require that these factors form a reparameterization of the problem. So this factor over x1 has to exactly cancel with this factor, so that when I add all these functions together, I get exactly the same model as before. Okay? And what we can do then is now we have exactly the same relaxed bound, maximizing individually within each factor, but now we have these extra reparameterization terms, and we can try to minimize over those reparameterizations. And you can think of these lambdas as being Lagrange multipliers that are trying to enforce equality of the choice of x1 and x2, for example. So in our initial relaxed bound, there's nothing to encourage the configuration of x1 for this factor to agree with the configuration of x1 for this factor. And we can use this reparameterization process to push them in order to agree. And so that will tighten this upper bound. So in fact, these two things are exactly Lagrangian duals of each other. So this linear programming relaxation that we wrote down is the dual of dual decomposition. I don't want to prove this to you, but I included this slide in case you want to go and prove it to yourself. It's quite straightforward. The trick is to simply take this, the consistency constraints that the sum over pairs of configurations needs to equal the individual one, and put a Lagrange multiplier lambda on those. And then when you rearrange and reverse the order of the maximization, then you'll end up with exactly this dual decomposition form, minimizing over the reparameterization lambda of a decomposed upper bound. Okay, so so this bound is very simple to think about, and then you can try to optimize this bound by tightening these Lagrange multipliers lambda. And in fact, this bound has been reinvented so many times that it has dozens of different names and different strategies for optimizing the bound. So most commonly nowadays, it's called dual decomposition, and often subgradient or something is used to optimize it. It's also equivalent to tree-reweighted max product linear programming, soft arc consistency, max sum diffusion. All of these algorithms are, in fact, optimizing exactly this same relaxation bound. When we optimize this, we can simultaneously get upper and lower bounds on our combinatorial problem. So this decomposed bound gives us an upper bound, and as we change this reparameterization lambda, we'll tighten this lower bound, hopefully toward the actual MAP cost. And at the same time, since we're getting configurations of each clique X alpha, it's very straightforward to try to pick a joint configuration X to evaluate. So any joint configuration X gives us a lower bound, since it must be less than the optimum X. And so we can just take the individual cliques and select, for each variable, select some clique to take that variable's configuration from. That gives us an overall configuration, and we can evaluate this objective. And so what we find is as we optimize this lambda, typically with the relaxation upper bound gets better and better. And as it does, this starts to expose what the optima of the variables are in each individual function, so that the configurations that we get as we pick some value for each xi get better and better as we go as well. And so as you optimize this and select configurations, you'll find that you have a lower bound from the configurations that you're finding that's increasing toward the map, and you have this upper bound on the map, and so you always have you can always get an estimate of your error tolerance between the best value you've found so far and what the possible gap between that and the true optimum is. Okay. So there are lots of strategies for optimizing these Lagrange multipliers lambda, and I'll just mention two of them very quickly. Subgradient descent is probably the most standard. It's very simple to do. So if we have this bound defined by maximizing the reparameterized individual problems, if we want to take the gradient with respect to these Lagrange multipliers lambda, it turns out that the derivative of this with respect to lambda depends on the value of x alpha that was selected. So, here's a small problem over x1 and x2 and x2 and x3. So the 3 by 3, each variable takes on 3 states. And just to illustrate how this works, the initial bound is given by choosing the optimum of this factor. So, sorry, these should be thetas. Optimum of this factor and this factor independently, right? So we have an initial bound that our MAP configuration must be smaller than 8. And the configuration that we chose for this factor was 1, 2, and the configuration we chose over here was 0, 0. Right? So, so the configurations of x2, which are shared by these two problems, are inconsistent between the two individual optima. So now if we take the derivative with respect to lambda, what we find is that we can decrease this, the contribution of this term, so decrease this term 3, by subtracting something from this row. And since we need for these two reparameterization factors to cancel, that means we'll have to add something to this row. But since this row is not involved in the maximum of that factor, we'll get a net decrease in the objective. So if we just, and similarly, if we want to decrease the objective here, since the optimum is this point, we can subtract something from this row. That'll end up correspondingly adding something to this row, but since that's not involved in our optimum, again, we get a decrease in our objective. So here I subtracted, say, 1 from this row and added it to the other. So lambda of x2 equals 0. I subtracted 1 from here and added 1 to there. And so now we get a new reparameterized pair of functions where we've used this function lambda to change the relative values in these two factors, but leave their sum unchanged overall. Then we can select the optimum of these two individuals. So now, since this one was decreased, now the optimum is some different point, and so we end up with a new bound corresponding to new configurations of the pair, and so on. And so what's actually happening here is the configuration of these factors, given the configuration of the optimum configuration of the two factors individually, the objective is actually linear in lambda. And so, so we start off at some position, and for fixed x star, we have a linear objective. We take a step to some new point. But this new value of theta might correspond to a different set of maximizers. So then we have some other linear function defined by that new set of optima. So this value is no longer the configuration 1, 2, 0, 0 corresponding to this line is no longer the maximizer. Instead, it's the line corresponding to 1, 1, 0, 0. And so we get a new point corresponding to a new bound. We can take another gradient step. So again, if we decrease this row and increase the row in our neighbor, it won't change the objective over here, but we'll decrease it there. Similarly, if we decrease this one, it'll increase that, but that won't change the objective. And so now we get a new reparameterization. And at some point, we'll end up with some form of agreement. So in this case, now x2 in both problems takes on value 0, so that there's an optimizing configuration of this factor and this factor that agree on their value of x2. And so at this point, the bound is tight. So, so now if I try to decrease, so if this optimizing configuration here, if I try to decrease the contribution of this row, I have to increase the row of my neighbor factor, and since the optimizing configuration is in that row, it will correspondingly increase. So now the gradient, the subgradient here is 0. Okay. So you can see that by doing this reparameterization, what you're actually ending up doing is exposing the configurations of x2 to both of these factors individually. Another approach to optimizing it is to use a fixed point algorithm. So this tends to look more like a message passing algorithm, which is going to be reminiscent of the other algorithms that we'll talk about. And so what we can do is we can choose some subpart of the model, like lambda of x2, and just optimize lambda of x2 directly to minimize the bound. So in this case, for example, we can directly minimize this bound over lambda 2 just by, for example, computing the maximum over x1 of this function. So here I'll call that gamma 1, 2. So maximizing for x2 equals 0, maximizing values 1. For x2 equals 1, it's 2.5, and so on. And then we do the same thing over here. So now this tells us what the best completion of x3 is for each value of x2 in this factor. And we know that this will be tight if these two things agree on which value of x2 is the optimum. And so one easy way to enforce that is to force them to both agree on what these max marginals are. So one way of doing that, so this is a max sum diffusion-like algorithm. We just take these two max marginals, find their average, and then reparameterize each of these factors to match this average. So here's the average of those two functions. And now if I just take this factor, subtract gamma 1, 2, and add gamma bar, I'll end up with a new factor that has exactly this set of max marginals. Doing the same thing to the other factor gives me this. And so what I find is that now I have a reparameterization of my original two factors that exposes what these that enforces that they agree on what the maximizing values with respect to x2 are. So in this case, you see that it's exactly the same solution as before. If I take the optimum of this table, I get 3. If I take the optimum of this table, I get 3. And so their sum is 6, just like before. So this is a coordinate descent where I've directly minimized over the entire function lambda, but for some pair of factors. So again, this forces these max marginals over their intersection to agree, which means that this is a more than sufficient condition to enforce that they'll agree on what the configuration of x2 that maximizes these two tables is. Okay, so so this reparameterization gives you a technique for tightening this decomposed bound. And here's just a very simple algorithm for optimizing it. Right? We just run over all the variables, collect together all the factors that involve that variable, and force them to agree. So this is going to be a coordinate descent on the decomposed bound, and you can get both an upper bound by individually maximizing all the factors, and also a lower bound just by picking some configuration of the xi's and evaluating it. So as you run this, you'll find that this upper bound slowly tightens and that the lower bound also increases as you run. Okay. So just to connect this back to trees and dynamic programming, it turns out that this linear programming dual decomposition relaxation is exact in any tree-structured model. So one easy way of seeing that is to just look at some tree-structured model. So if we have this simple chain, and I do variable elimination to compute the optimum via dynamic programming, right? I'll eliminate over x3, so I'll get some function of just x2 that eliminated over x3. Then I add that to theta 1, 2 and eliminate over x2, and then I can eliminate over x1. So this is just a variable elimination 3, 2, 1. There is a reparameterization that gives this exact value for the decomposed bound. And so just a simple construction that will do that is to just reparameterize this factor to be itself minus the message that we computed. And then this factor will be itself plus the incoming message from 2, but minus the outgoing message, M1. And then tack M1 down here on the bottom. And what you'll find is that the contribution of each of these things is actually 0. So if you run this decomposed bound on these parts, the maximum with respect to x2 and x3 together of this function is guaranteed to be 0, because this value was the maximum of x3 with respect to that. And so their difference is going to have some 0 in every row. And so then computing this decomposed bound, you extract only this one term. So this just shows constructively that there is some reparameterization that achieves the optimum value in this tree. And since our coordinate descent, it's a convex optimization problem, the procedure, for instance, the subgradient descent that I described will find the same optimum. Maybe not this reparameterization, but exactly the same value. Okay, so this decomposed bound is exact on trees. Okay, so the connection of that to elimination we'll come back to, but you can see that this reparameterization is very closely related. Since we're in the mini bucket bound, we were decomposing some of the variables into parts and then thinking about reparameterizing. And this is very similar. We've over-decomposed it and then reparameterized as well. So the last thing I want to talk about here is the variational interpretation to this, which is another useful perspective to have and connects closely to this linear programming form. So variational algorithms variational methods are things that replace the variable elimination process with an optimization over distributions, so some kind of functional. So in maximization, this is a fairly easy example to see. So in maximization, we want to find this configuration X star that finds the optimal configuration of the entire system. The variational form of that is an optimization over distributions. So we optimize over all possible distributions Q of X to maximize the expected value of log f of X. Okay? So this seems a little strange at first, perhaps. But it's easy to see that these two things are equivalent, because the optimal value of Q for this distributional optimization will just put all of its mass on the optimum X star. So if I'm finding the distribution Q that maximizes the expected value of log f, if I put all my mass on X star, then this value is just log f star. And if I put any of my mass on any other configuration with a smaller value of f, then this expectation will average those two and decrease the overall total. So, so the distribution that's going to maximize this expected log f is just a delta function on the true configuration x star. So this doesn't seem like it helps particularly, but it's going to give us a new way of framing approximations. And so if you think about q being some function in the exponential family, sorry, f being some function in the exponential family, so f is a sum over these theta factors, then the optimization over distributions q depend only on the expectations over q of these indicator functions that we saw. So in fact, when we optimize over q of this expectation of log f, this log f is going to decompose into a sum over thetas. And so we really only care, we don't care about the entire distribution q. It's enough to just think about the probabilities of q defined on these smaller cliques alpha. And so another way of writing this optimization over distributions q is to optimize over marginal probabilities mu that are consistent with some joint distribution. And so we can think of the set of mu's that are consistent with some joint distribution q and call that the M, the marginal polytope. So M is the set of all possible marginal probabilities that are achievable by some distribution q. Okay. So this concept of the marginal polytope M is a useful one to have in your bag of tricks. And you can think about what set of moments are possibly achievable by some distribution q. It's easy to see that this is actually a polytope, an intersection of half-planes for a discrete system. So if we have, say, an exponential family problem, so I'm just going to write a simple distribution over a pair of variables x1 and x2. So any distribution over x1 and x2 is just representable by 4 probabilities. So it's binary. And so the marginal probabilities over those over our indicator vector u will just be those probabilities q for each possible outcome. And then the constraint on these probabilities is that they need to sum to 1. And so the polytope here is then just the unit simplex, right? So each vertex of M corresponds to some configuration of X. So each vertex is a configuration of the system. And then the set of achievable probability distributions is just all the convex combinations of that, right? So any distribution Q is some convex combination of probability masses on the outcomes of X. So each vertex corresponds to some indicator function, and since Q of X will put some weight on every configuration X, then the set of all possible probabilities corresponding to some Q is just the convex combination of those vertices. So in this case, it's this unit simplex problem. So M is a polytope in discrete variable systems. In general, it turns out to be a convex set. So I'll just mention this for the Gaussian case. In the Gaussian case, it's not a polytope, but it is still convex. So the exponential family has 2 features, x and x squared for Gaussians, and the expectation of those features is the mean and the uncentered variance, the second moment, which is the variance plus the squared mean. And if you think about the set of possible values of these two moments that can be achieved by any Gaussian distribution, well, the mean can be anything. So the mean can be anything on the, so we'll put that on the x-axis. And then this second moment is some non-negative variance plus the mean squared. So the set of possible pairs, mu1, mu2, corresponding to any Gaussian is this convex quadratic set. Okay? So in general, the set of for an exponential family model, the set of possible moments that can be achieved by some q is a convex set. And mostly we will think about discrete problems where it's a polytope. Okay, so how does this viewpoint connect to linear programming and dual decomposition? If we have this discrete optimization problem, the variational form is an optimization over distributions Q of the expected value of theta. And so that's a maximization over probabilities that live within this marginal polytope of this linear form. So unfortunately, there are a lot of constraints on these possible marginal probabilities. But if we only enforce some of them, so for instance, here's a subset of things that any probability vector mu must satisfy, right? Certainly, all the probabilities need to be between 0 and 1. The probabilities over xi need to sum to 1. And the probabilities over xi and xj jointly need to sum to 1. The probabilities over xi and xj marginalized over xj must equal the marginal probability of xi, and so on. So we call this the local polytope because while it's not enforcing all the possible consistencies, it's enforcing local consistency between pairs xi and xj and individual variables xi. This relaxation, so if we relax this set M to just be this local consistency constraint, we get exactly the linear programming relaxation we had before. So these constraints are exactly identical to the linear programming constraints that we had a few slides ago. So this is a sort of interesting different perspective on the linear programming relaxation, in that when we wrote the integer linear program and relaxed the integrality part to get the linear programming relaxation, adding that integrality constraint is relatively hard, right? So it's difficult to add back in something like an integrality constraint. But here, these are actually just linear constraints. It's just that there are quite a lot of them. So now we can actually tighten this linear programming relaxation just by starting to add back in constraints over this marginal polytope. So this is a sort of common visualization of this. The marginal polytope M has vertices corresponding to the configurations of the discrete system. This local polytope relaxation may have additional vertices that don't correspond to any true distribution. And so so this L is an outer approximation to M, which relaxes this constraint set. So this local polytope may have things in it that don't correspond to real probability distributions. And to just see that as an example, here's a trivial problem with 3 variables again. So I'll specify a collection of marginal probabilities that are locally consistent but don't correspond to any actual joint distribution. So x1, x2, and x3 will all just be a half, so equally probable. X1 and X2 will have probability a half on diagonal, so probability a half that they're both 0 or a half that they're both 1. And so you can think of this as just a constraint that X1 equals X2. Same thing for X1 and X3. And then for X2 and X3, I'll put them on the off diagonal. So this is enforcing that X2 and X3 will take on different values with the probability half of either pair. And so then it's easy to see that there's no consistent configuration that satisfies these constraints, and therefore there's no distribution that satisfies these marginal probabilities. Right, so we can't have X1 equals X2 and X3, but X2 and X3 aren't equal. So this is actually, if you're familiar with things like arc consistency in search, this is exactly the relaxation of arc consistency. So in arc consistency, we reason about local relationships in the constraint system, and we enforce that they need to be locally consistent. But even once we've enforced that local consistency, the system might not be globally consistent. So if you don't like this example, you can relax it so it doesn't have hard zeros anymore and get a similar example. But this just shows that enforcing this local consistency between the pairs is not really enough to ensure that we correspond to some joint distribution. On the other hand, for tree-structured graphs, it actually is enough. So suppose I have some arbitrary probabilities within this local polytope, and where I'm specifying them only on the edges of a tree-structured graph. So here I have marginal probabilities for X1, X2, X3, and so on. I have marginal probabilities for the pair X1, X2, X1, X3, and X1, X4. And I ensure that those marginal probabilities for the pairs are consistent with the individual ones. So if I marginalize P of X1, 2 down, I'll get P of X1. Okay? So this is just the local consistency constraints, but only specifying joint probabilities on this tree-structured collection of edges. So then it's easy to see that there actually is a distribution that corresponds to these probabilities. Whoops. So just so choose some root like X1, and then work downward, creating conditional probabilities. So for instance, I'll choose Q of X1 to be my marginal probabilities that were specified. Then I'll choose the distribution of X2 given X1, and I'll just use the chain rule for conditioning. So I'll use my marginal for the pair and divide by the marginal for X1. And then I know, because of this pairwise consistency, that this, if I multiply by Q of X1 and marginalize to X2, it will also be consistent with mu2. Okay, so if I have any collection of consistent pairwise marginals specified only on this tree, I can actually create a distribution very easily that satisfies those. And effectively what's going on is that I'm building outward along the edges of this tree, and because no moments have been specified off of this tree, I won't find any contradicting settings. So once I've set X1 to X3 and X1 to X2, I don't have a specification of what the marginal probability of X2 and X3 together are. So I don't have to check that some distribution corresponds to that moment. So as long as I only specify these moments on a tree-structured graph, then enforcing the consistency of the local polytope is actually enough. And so this actually just shows exactly the same thing we saw from a different perspective. So since this local relaxation is exactly the marginal polytope for tree-structured graphs, and this local relaxation corresponds to the linear programming relaxation, that means that the linear programming relaxation must be exact on trees, since we're relaxing M to L, but it's not actually a relaxation of any kind. It's exact. Okay, so so this just shows several equivalent views of the same maximization relaxation. Right? We have mini bucket, which corresponds to variable elimination, but taking approximate steps where we've relaxed the configurations of variables that were being eliminated. This is closely connected to dual decomposition. So we're duplicating variables in each and then using reparameterization to tighten the bound. This is the dual of the linear programming relaxation, and the linear programming relaxation can be viewed as a variational form where we have an optimization over distributions, except that we've relaxed the constraints on those distributions to have only a local consistency. So the key sort of takeaways here about all of these methods is what's really critical in the approximation is just the region and intersection choice. So what cliques of variables will I reason about jointly? So again, looking at this mini bucket relaxation, when I decided to reason about x1 with x2 and x3 together, effectively I'm deciding on these groups of variables to reason about jointly, and then using reparameterization to try to optimize the bound that's formed by those groups. So the two key tricks are selecting what our regions and intersections will be, and then using reparameterization to try to expose the optimum of the joint system in terms of only those individual cliques. Okay, so that takes us to the coffee break, so I think we'll take a few minutes and come back shortly. I'm sorry? Oh, yeah, sure. Yeah.
So since we have a few minutes before the break starts, do any of you have questions for Alex? So in that case, I have one. Which, like with all these different ways of expressing the problem, do any of these approaches yield better algorithms in the end?
So they're all fairly equivalent. Typically, the fastest converging stuff are these fixed point coordinate descent algorithms. And so actually, this kind of coordinate descent-like thing, where you compute max marginals and then do reparameterization to fit, is exactly what I use in things like mini bucket as well. So in fact, what something like mini bucket will do is define these cliques, and then all that really matters are the definitions of the cliques. Whoops. So once these cliques have been defined, you can just do this fixed point operator to try to tighten the mini bucket bound as well. So in fact, this is what we use for creating search heuristics for depth first search, and it's terrifically successful at tightening the heuristic function. We had I did some of this in collaboration with Rena Dechter and her group, And we won the UAI competition. I think, I guess we won all categories of maximization in 2011, and then I think we won a couple of categories in 2014. So it really is extremely fast at tightening. Yeah. Sorry, can you speak louder?
Yes, so there's a subgradient MAP, right?
Mm-hmm.
For optimizing the graph maps. And so you were subtracting these rows each way to the right. So these were actually gradients with respect to the matrix.
Yeah, so the gradient with respect to this objective is 0 except on terms that involve this the maximizing configuration. And so if I want to decrease this objective, the sum of the maxima, the only way to do that is to decrease this row, which will increase this one, but that doesn't contribute anything to that side.
Okay, and how do you determine how much? How do you determine the degree? Like,
Oh, that's just a step size. It's gradient descent. So gradient descent sucks.
but you call it gradient descent, but it's not actually like you're not differentiating anything.
I am differentiating, yeah. Take the derivative of this thing with respect to lambda of x2 equals 2. Right? What you'll find is that either the derivative will be 0 because it doesn't depend on it because it's not the maximizing configuration, or it'll be constant. So, you know, it literally is differentiation.
Okay, if there's no other questions, we'll be back here at 10:50.
We've talked about maximization perspectives and approximate maximization problems. Let's talk about approximate summation, marginalization problems. In particular, probably the most popular method is loopy belief propagation. And so that's what I'll start with and then talk about its connection to variational ideas. So, so summation problems work exactly the same as maximization in terms of variable elimination. So again, in trees, we can always find some leaf, say x1, eliminate over it, inducing some smaller function over only its neighbor, and so on. And so the summation problem, at each step, we're doing the same kind of procedure that we were doing in maximization. We're eliminating over some variable of collecting all the functions over the eliminated variable together. And so in a tree, this has a very nice form. Probably the best example is this one. When we go to eliminate over, eliminate over x4, we collect together all the factors that involve x4 as well as all the messages. And so our form is a summation over x4, a product of the pairwise function over x4 and its upward neighbor, and a product over the messages. And so this can be written in this nice, compact way. In factor graphs, so if we have more general non-pairwise factors, we can do exactly the same thing. And the calculation is frameable in this kind of message passing way. So we can have a message from each variable I to its clique alpha, which is a function of xi itself. And that's just a product of all the incoming messages except the one from alpha. So here, for example, to send a message from x2 to f123, I would take the incoming messages from my neighbor 24. And then messages from cliques to variables are also functions of the variable itself. And those correspond to just eliminating all the variables in x alpha except xi of the factor f alpha times the product of messages. Okay? So you can verify that this message update scheme is exactly the variable elimination form that we get from just eliminating sequentially. So for example, here, to get a function over x1, I eliminate over x alpha, 1, 2, 3, not including x1, of the product of the incoming messages into that. So here I have a message coming from x3, another message coming from x2. I take their product, and I eliminate over 2 and 3 to get a message over x1. So we can also use this to compute marginal probabilities just by, so the marginal probability will just be a normalized version of the functions over x1. And if we're interested in computing other marginals, like say the marginal at x2, I can do it exactly the same way, except with a different elimination order. So we eliminate x4, x3, and x1 inward to x2. And what you find is that if you do this, you end up reusing a lot of your computation. So the message from x4 to x2, for example, is the same to compute the marginal over x2 as it was as the early part of the computation to find the marginal over x1. So in fact, typically, if we want to compute the marginals of all the variables, we can do it just by a two-pass message procedure. So we move from leaves to root, so to some root, and then back from root to leaves, calculating the red messages inward and then the yellow messages back outward. And once we've calculated those messages, we have all the messages that we need to calculate any marginal. So if we want to calculate the marginal at x4, for example, treating this as a rooted tree at this point, we just need this yellow message coming inward. If we want the marginal at x2, treating it as a rooted tree at x2, we need the red message this way, and the yellow message this way, and the red message that way. So these messages summarize the marginalization of the tree rooted at that point. So for example, if I root away from x2, these messages are summarizing the marginal of the model below that point. And then once we've calculated these messages, we can calculate the marginal at any variable just by taking the product of the incoming messages and normalizing it. Similarly, if you want the marginal of any cliques, you can take the incoming messages to that clique and normalize them. So once you've observed that this procedure is just a calculation of messages in a self-referential way, so a message from I to its neighbor alpha just depends on all of the neighbors of I except for alpha. You can observe that you can actually calculate this in a way that doesn't depend on this tree ordering anymore. So although we derived this by eliminating from the leaves down to the root and then back outward, we can actually just update all of these in a parallel fashion where each message depends on the previously computed messages from the neighbors. And so what will happen if we calculate it like that is at the first iteration, none of the messages will initialize the messages to something. None of the messages will be correct except for the leaves. At the first iteration, the leaves will correctly calculate their messages to their neighbors. And at the second iteration, their neighbors will be correctly calculated, and so on. So eventually, if you do this enough, you'll move with correct calculations from the leaves into the root, and vice versa. But once you have this perspective of just local calculations, you can actually just apply the same local updates even to graphs that aren't really tree structured anymore. So here's a graph that's very close to the tree I had before, but now I have an extra factor. I can still apply these message passing recursions where each message depends on the other messages in the system, and just not worry about the fact that this is no longer a tree. So this is an algorithm that was originally proposed by Judea Pearl back in 1986 in his book. He called it belief propagation. And it sort of languished unlooked at for a long time. until in the late 90s, there was a lot of excitement of error-correcting codes around a technique called turbo decoding, which then my colleague Porrick Smith showed was an instance of Pearl's belief propagation. So this got everyone extremely excited about belief propagation. There was a whole series of papers of people who would just try belief propagation on different problems and discover that it worked really incredibly well. So this, if you apply this recursion in a non-tree structured graph, you can still calculate your marginals in the same way as before, but now the calculation is no longer correct. So we don't call them marginals, we typically call them beliefs, because they don't correspond to the true marginal probabilities of the system. Since it's now no longer tree structured, you have cycles, and so the system may actually not converge. This is just a set of fixed point equations that describe your update procedure. And because of this, the initialization of the system and the schedule of updating can matter quite a lot. It's only approximate, so these beliefs we're going to hope are something like the marginals. But in fact, in practice, it turns out to work really well. And the quality of it depends on how tree-like the model is. So just as a quick illustration of how shockingly good this is, here's a graph, a small Ising grid, where I generated some random potentials and ran loopy belief propagation. And these are the actual true probabilities, and these are what loopy BP converges to, which is not quite correct, but very, very nearly. So even though this graph is significantly non-tree structured, the model is simple enough and the algorithm is good enough that its marginal probabilities are quite accurate. Okay, so why does this work? There are a few ways of understanding loopy belief propagation. There's a sort of procedural way, which is to just think about its calculation. Each message that's being computed is computed from the message from your neighbors at the previous iteration. So if I want to think about the belief at some node 1, I'm computing that belief based on the product of incoming messages from my neighbors 2 and 3. And the messages from 2 is computed from the messages from its neighbors not including 1, so 4, and so on. And so I can think about creating this unrolling of this model that just calculates how this message came about. So the belief at 1 was gotten by messages from its neighbors 2, 3, and 4. And the message from 2 was gotten from its neighbor other than 1, so 4. The message from 4 from its neighbors other than 1, 2, and 3, and so on. And so, the loopy message passing in this graph with cycles can be viewed as just an upward sweep of exact inference in this rather strange thing called the computation tree. So in fact, if you initialize your messages at the leaf nodes here in the same way you initialize them in the loopy model, in the first pass of message passing in the loopy model, you'll calculate the messages going to this level of the tree. The second pass of messages, you'll calculate the messages at this level of the tree, and so on. And so what this means is that you can understand loopy BP's behavior by the connection between the original model and this strange expanded model. So if the original model and this expanded computation tree are quite similar, then loopy BP will tend to be accurate. And so the conditions for that tend to be things like if the relationships in this graph are very weak, so the difference between this graph and this tree is that, for instance, 1 appears twice. There's here 1 is correlating with itself through this red path. But if the relationships here, 1 to 4, 4 to 2, and 2 to 1, are relatively weak, then this will look fairly tree-like compared to this. And so, in fact, this turns out to be quite similar to things like mixing rates in Markov chains. Or if we have very strong evidence about some of the variables. So if we know very nearly the values of our neighbors, then that will create a Markov blanket that cuts this node off from its cycles and makes it accurate. Okay, so Loopy BP is originally was described as this rather procedural way of computing these marginal probabilities. But I mentioned before, we also want to calculate the partition function, the normalization constant of the distribution. And so what's the connection between Loopy BP and this partition function? It turns out that this variational idea gives us the way of connecting those things. So, so the log partition function also has a variational form, very much like the variational form for maximization. So it's the partition function can be formed as an optimization over distributions Q of something similar to maximization, so the expectation of log F, but now plus an entropy term. And this is actually fairly easy to prove if you're familiar with the KL divergence. So the Kullback-Leibler divergence between two distributions Q and P is just the expectation under Q of log Q over P. And here P is our normalized version of F, so F divided by the partition function. If you just rearrange this, you'll get Q log Q, which is the negative entropy of Q, minus Q log F here, plus Q log Z, but since that's a constant, that's just log Z. And the KL divergence between two distributions is the pseudo distance between those distributions. It's always non-negative. And so, so since this is greater than 0, we can move log Z over. We find that the partition function is always larger than the expected value of log F plus the entropy. And this divergence will be 0 if and only if Q and P are the same almost everywhere. So in fact, this inequality will hold with equality if Q is equal to P, meaning Q equals the normalized version of our model F. So this gives us now a variational form for the partition function, an optimization over distributions. And just to compare it with the maximization, right, maximization only had this expected value of log F. So the Q distribution that maximized it was something that put all of its mass on the large value of log F, right, the optimum value of X. Now we have an extra term, the entropy of Q. And so we're going to balance between configurations X that have high value and distributions that have high entropy. And so, so now our optimal Q won't be a delta function at X star. It'll be something that spreads its probability mass out according to the relative probabilities of F. So using this variational form, now this actually doesn't help us that much immediately because we have two fundamental problems. The first is that maximizing over this distribution Q is very hard, right? Just like before, specifying the set of all distributions is quite complex. And secondly now, in addition to this term, which decomposed nicely for the maximization problem, we now also have an entropy. And the entropy is defined in terms of the joint distribution Q, which isn't really available to us, right? We never want to specify Q because it's an exponentially large function over the state space X. So what we'll want to do is we'll use our trick from before about breaking this part up into smaller components. And now we'll approximate H in some way that decomposes according to those smaller parts. So we'll typically substitute this entropy of Q with something that's easier to evaluate in terms of being defined only in terms of low-order moments, meaning probabilities of small cliques of the system. So that way, when we relax our marginal polytope to something like the local polytope, our approximate entropy H should also be evaluatable by any set of probabilities in the local polytope. So it turns out that one possibility is what's called the Bethe approximation, and this is going to correspond to Loopy BP. So the Bethe approximation approximates the entropy of a distribution in terms of only its low-order entropies. So we sum over all the variables of the entropy of each variable individually, and then subtract the mutual information between pairs of variables in the edges. And so HI is the entropy of XI, and IIJ is the mutual information, so the cross entropy between the probability of XI, XJ, and its product of marginals. So why is this a reasonable thing to substitute as an entropy approximation? In tree-structured distributions like this, it turns out to be exact. So if we have a tree-structured distribution, then our probability decomposes. So here I'm writing a Bayesian network, so I have a P of x1, P of x2 given x1, and so on. And so we can reframe that to be, say, the P of x1 times P of x2 divided by P of x1, x1, x2 divided by the product. Right, so this conditional expansion, 1 and then 2 given 1, I can rewrite 2 given 1 as the joint divided by P of x1. And then if I make it a symmetric form, I can write the product of their individual marginals divided by times this mutual information-like form. So then the entropy of this system actually has exactly this Bethe form. So now if I take the expectation of log of this probability, right, the entropy of this form, I'm going to get an entropy of x1, an entropy of x2, and then this mutual information term here. So if you know the Chow-Liu algorithm for learning probability models in Bayesian networks, this rearrangement of things in terms of entropy of individual variables and mutual informations between pairs of variables is exactly the same trick that Chow-Liu uses to prove optimality. So this will only be correct in models with no cycles because it relies on this sequential expansion. It relies on the fact that each pair appears only in one edge. But we can use it as an approximation in graphs with cycles called the Bethe approximation. And the connection of this work from statistical physics to belief propagation is actually due to Jonathan Yedidia et al. From 2001 or so. So if we use this, we can substitute it into the variational form. And now we have an optimization over distributions under some, say, relaxed set of constraints. So we want to optimize over probabilities that are at least locally consistent with one another. We have the expectation of log F term. So these are just the expectations of our small cliques. And then we have our approximate entropy term. So instead of an entropy of a joint distribution, the entropy now decomposes. It's approximated by decomposing it into smaller terms, each of which depends only on the beliefs of these local cliques. And then this local polytope is just this collection of marginal probabilities that are locally consistent with one another. So every probability needs to sum to 1 and be non-negative. And probabilities over pairs of variables should marginalize down to their individual probability. So then if you use, excuse me, if you use exactly the same Lagrange multiplier trick that we did to show the linear programming to dual decomposition form, so we write one Lagrange multiplier for each of these consistency constraints, that the marginal of this pair equals the singleton probability. You get a Lagrangian, and if you then solve that, you'll find that, so call those Lagrangians lambda. You can solve for the lambdas, and you'll find that they form exactly the same fixed point equations that loopy belief propagation had. So if you exponentiate the Lagrangians of this, Lagrange multipliers of this optimization over entropies subject to these constraints, you'll find that the Lagrange multipliers exactly satisfy these fixed points of belief propagation. So, in fact, optimizing this approximate entropy objective subject to local constraints exactly gives us this loopy belief propagation algorithm that came from intuition before. Okay, so that gives us a way of using these beliefs to try to estimate the log partition function. So we can just run loopy belief propagation to calculate the marginals, the approximate marginals. If we find a fixed point, then it's if we find a fixed point of the system, excuse me, then it's an optimizer of this Lagrangian, and then we can use the beta approximation to estimate the log partition function. So if we have these beliefs, it's easy for us to compute the expected value of each factor, each log factor, and then we can add on this approximate entropy term. So the entropy of the individual variables minus these mutual information terms. So this is a sort of pairwise expression in terms of entropies and informations. Sometimes you'll see it written in terms of counting numbers of entropies as well. So the log partition function is written as the expectation of log f plus a sum over local entropies of each clique alpha times some counting number C alpha. So in this case, this and this correspond if we just take each so expectation of B alpha log B alpha, so this is going to be the entropy of B alpha, so that'll have counting number 1. And then BI will be included once, but then removed a number of times corresponding to how many times I enters into alpha. So here our counting numbers are 1 for each clique alpha, and then for each individual variable, it's 1 minus the number of factors that xi participates in. So again, what you can see from this form is that just like in the linear programming and dual decomposition form, what actually matters are these regions that we're going to approximate with. So we're going to be computing beliefs or distributions over some cliques, alpha, and our expansion depends only on the expectation of our factors under on those cliques and entropy terms that are also defined on those cliques. So now, instead of with the linear programming and dual decomposition, the cliques defined only the set of constraints that we were enforcing, the local consistency constraints. Now they're going to define not only the local consistency functions, but also this entropy approximation. So in fact, you can define fairly complex sets of entropy approximations. For example, things like region graphs. So if I have a grid like this, rather than using the original factors, I might decide that I'm going to represent larger cliques as well, in which case I'll think about defining distributions on, say, sets of 4 variables, maybe the faces of the grid at a time. And I can define an entropy approximation in terms of this as well, where I have entropy terms for each of these cliques, and then I look at the intersections of those cliques and the intersections of those, and I have an entropy approximation defined on all of these sets of variables. So then I'm going to have consistency relationships that my distribution Q should have marginals defined on each of these 4 cliques, and that the marginals defined on each 4 clique should agree on their intersections, and those should agree on their intersections, and so on. And then in addition, I'm going to have an entropy expansion defined on those. So typically, the way that you can set these counting numbers, you choose your counting numbers for the largest regions to be 1, and then you can just set the counting numbers using inclusion-exclusion. So you want every region to appear exactly once in the overall entropy expansion. So if I include this region once and that region once, then I've included their intersection twice, so I need to remove it. Yeah, I need to remove one, right? I want this intersection to appear only once, but it's included twice. So I give it a counting number -1, so I'll remove it. And then if I run through the individual variables, for instance, x5 was included 4 times here, and then unincluded 4 times, so I need to re-include it 1 more time. So you can set these counting numbers via this inclusion-exclusion so that each region appears once. So you'll set it equal to 1 minus the counting numbers of all the regions that already included it. So once you have these variational forms, you can define all kinds of approximations that, that will help you accurately approximate or bound either the objective or the partition function. And so we saw for maximization, pretty much everything corresponded to this linear programming decomposition view, where we had relaxed the set of all distributions to locally consistent marginals. And so we got an upper bound on the true objective. We have a lot more degrees of freedom in terms of the partition function, because now we have not only the consistency, but also the entropy approximation. So different choices will lead us to different approximations or bounds. Belief propagation, I mentioned, is this beta approximation to the entropy and a local polytope relaxation. But we can actually get upper and lower bounds using things like tree-reweighted. So tree-reweighted relaxes the set of constraints and uses an upper bound on the entropy. Mean field uses an exact entropy and an inner bound. So we'll see how these work in just a second. Excuse me. In order to talk about this, I need one more property of the partition function, which is that the partition function, viewed as a function of this vector theta, is a convex function. So remember, our model is specified as this vector theta in exponential family form. And the log partition function, so log-Z, is a log sum exp of this form. So here, theta is our log model. So e to the theta is our function f of x. Summing it marginalizes, computes the partition function, and then taking the log. This log sum exp operator is a convex one. So if we view this as a vector space of models and think about how the log partition function changes as we change the model slightly, that log partition function forms a convex function. A nice view of this comes from taking the derivatives of this log partition function. So the log partition function here, log sum exp of our model, if you take the derivative of this with respect to a parameter theta, what you find is you're going to get 1 over sum of e to the theta times the derivative of e to the theta. So this derivative actually ends up computing the expectation of that particular feature. So in fact, the derivatives of the log partition function are the marginals of the distribution specified by theta. So, so if we're at a particular model theta and we look at the derivative of the log partition function, it's actually the marginal probabilities of our model. And in fact, the second derivatives correspond to covariance structure, which is another way that one can prove that this is a convex function. So this convexity property gives us a nice way to get upper and lower bounds on this partition function. Okay, so so first I'll look at lower bounds with mean field, and then I'll look at lower and upper bounds using reweighted methods. So here's our variational form. That the true log partition function is the maximization over distributions of this expectation of theta plus entropy. Right? So the actual optimum will be at the true distribution p. But if we restrict ourselves to, instead of maximizing over all possible distributions, we just maximize over distributions where this entropy term is relatively easy, then we're going to get a restricted maximization. So we're going to get a lower bound on the optimum. So for example, if I restrict my attention to distributions Q that are fully independent, so Q is a product of distributions on each xi, then this entropy over Q is easy to evaluate. Since Q is a product, the entropy is just the sum of entropies over each variable. And so that means that my entropy is also expressible in terms of these of just simple probabilities. And then we can optimize this bound by searching over Q's to maximize this distribution. If you do this, you could do any kind of optimization you like, but if you do a coordinate ascent, for example, it has a very nice form. So maximizing over 1 Qi, given the rest of this objective, the only terms that depend on Qi are the expectation of any of these thetas that involve xi. So we're going to get only the rest of them will be constant since we've fixed the other q's. So we're going to get only the expectation of the factors that involve I, so the factors that are neighbors of xi, plus an entropy of qi. Yeah. I'm sorry, can you? The entropy is a function of the distribution of x. Yeah, I use slightly different notations sometimes. So, yes, right. H is a function of the distribution of x, not of a value of x. This one? Mm-hmm. Yeah, so the actual log partition function will be the optimum of all possible distributions. The true optimum will be achieved by P, the model that's defined by theta. So in mean field, we're going to restrict this optimization to a smaller set of possible Q's. So the true P won't be in that set, but we'll maximize over that set and get a lower bound. It's, yeah, maximizing over Q of this objective function. Yeah, right. And H is the entropy of the distribution Q. Yeah. Yeah, sorry, this notation is just, sometimes people write H of X and Q is hidden. Sometimes people write H of Q and ignore x. And so I usually try to write this, but sometimes I use shorthand. Yes? I'm sorry, could you say again? You could optimize this however you'd like, actually. I'm just showing the most standard method is a coordinate ascent because it's going to result in a message passing like thing again. But you could actually optimize Q in whatever way you like. So Q is just specified in terms of these marginal probabilities of each xi. You can think of just vectorizing this and then optimizing it directly. So this is sometimes used in expectation maximization, which I'll show in just a second, actually. Other questions? Okay, so the coordinate ascent version of this, if we update just one qi, so the distribution of just xi, fixing all the others, this expectation, the only terms that depend on qi are the theta, the cliques that include xi. So we're going to get an optimization over qi of the expectation of this stuff, alphas that involve I, plus the entropy of qi. Okay? And so these theta alphas depend on other x's other than I, but their expectation is already being taken with respect to those. Those q's are fixed. So in fact, you can just define, say, log gi to be the expectation of all the other variables of these terms. So this leaves just a function of xi. And then, sorry, this should be expectation over qi of this plus h of qi. Sorry, there's a typo. And so that expectation of this plus h of qi is actually just a KL divergence between g and q. And the KL divergence is going to be minimized by matching qi to g. So in fact, the optimal value of qi is just to set it proportional to this exponentiated expectation of the local functions theta. So to update each qi, we fix all the other qj's. We calculate the expectation of our neighboring factors alpha under those qj, giving us a function of just xi, and then make that a distribution and normalize it, and that becomes q. So here's a quick demo that I think sheds some light on what mean field is doing in some sense. So here's a pretty trivial model. It's just a function over x1 and x2. So it's just a two-variable model. And I'm going to fit mean field using a product q1 of x1 times q2 of x2. Okay, so here's my, my log factor over x1 and x2 jointly. And you can see most of the, so this is the log factor. So it's e to the 3 in the 1, 1 position, and e to the 0, so 1 in the 0, 0 position. So the log partition function of this model is about 3.24. And if we initialize any distribution q, our form, where was it? For any q, the expectation of theta plus the entropy of q is going to be less than log z. So even this q, this q that I start off with, if I take its expectation over the model plus the entropy, I end up with a lower bound on log z. It's about 2.5. So then this coordinate ascent, what we can do is fix Q2 and take its expectation, so take the expectation of our neighbor 1, 2 over that thing to get a function of x1. And then, so if you do that, expectation of this over that gives you a function of x1. If you normalize, exponentiate and normalize that to be a distribution, you'll get your updated version of Q1. So we update Q1 to be that. And our newly updated Q1, Q2 product has now increased the log partition function lower bound. If we then fix Q1 and take the expectation and get a distribution over x2 and normalize, we'll get a new value for Q2, increasing the lower bound still further. And if you iterate over this, eventually you will converge to some local optimum. Since this is coordinate ascent, it's guaranteed to converge. And whatever it converges to will be a lower bound. I think there's a useful intuition here, is that mean field is essentially fitting a distribution underneath log f. So what's actually happened, so the converged distribution that we found here, Q1 times Q2, has it's an independent distribution with most of its probability mass on 1, 1, right? So 0.9 times 0.87 or so. Effectively, what mean field is doing is finding a simple distribution, a product, that fits under some mode of f. So here f is very simple. It's got most of its probability mass over here. And so what mean field has done is stick most of its probability mass here as well, and then have its the probability in the rest of the model is independent. And so what this lower bound is effectively doing is finding some mode of f that can be fit underneath using this product form, and then using finding the probability mass of that mode as its lower bound. So if your true model looks almost like a independent distribution, then your bound will be quite good. And if it looks very different than an independent distribution, it might be quite bad. Another viewpoint of this is given from this marginal polytope view. So mean field is giving us an inner bound on the set of all distributions, right? The set of our mean field distributions are the set of distributions that are in product form. So not all distributions have this form. So this is a restriction of our distribution Q to this subset. The difficult thing about this is that it's actually a non-convex inner bound. So this is the usual drawing, right? Every vertex, every configuration X has a form like this. So if I have a Q of X as a delta function over some configuration, that's easily expressed as a product form. It's just a product of delta functions. So every vertex of the marginal polytope actually lives in this mean field set. But if you view our parameter vector theta, the set of distributions in this is actually a non-convex shape. So if we have x1 being expressed as q1 and x2 being expressed as q2, then when we get to the terms that involve interactions between x1 and x2, right, we have some entry of probabilities for the pairs. These probabilities have to be the product of these singleton probabilities. So in fact, this part of theta is being restricted to some quadratic shape, like this. So this set includes all the vertices, but then restricts ourselves to some non-linear submanifold of the parameters theta. Okay, so this is why this is one reason why this coordinate ascent is not globally optimizable. It just finds local optima. A third viewpoint of mean field that I think is useful comes from this convex form of log-Z. So suppose we wanted to evaluate some log partition function of some model theta, right? This is what we want. What mean field is actually doing is finding another model that's nearby, but has an easy to evaluate form. So suppose this is the theta we're interested in, but nearby is a theta that is an independent distribution. And so it's easy to evaluate the log partition function. So this point is easy for us to evaluate. And the derivatives at this point, the gradient of this log partition function, are just the marginal probabilities of that model. So now we have the value at this easy to evaluate theta prime, and also the tangent plane at that point. And this gives us a very simple linear lower bound, which is mean field. So we can lower bound the value at the theta we're interested in by just using its value on the tangent plane. So we use theta prime's tangent plane and evaluate it at theta. So the partition function at the target theta is less than this linear expansion around theta prime. And if you just follow through that through, you find it's exactly the expectation under your model theta prime plus the entropy of theta prime. So these are the moments of the easy distribution. Okay, so this gives you another viewpoint of why mean field is a lower bound. We're doing a linear approximation of our partition function. So then this coordinate ascent procedure I was describing is essentially just trying to find the best theta prime. Right? You want a theta prime that's as close as possible to theta so that its tangent plane will be close once we do this linear expansion. Okay. So mean field is often used in variational learning. For example, variational forms of expectation maximization. So in EM, we're trying to optimize some model parameters theta to fit some collection of data. And we have some hidden variables Z. Right? We have some observed empirical distribution given our data X. We have some hidden variable Z, and we have some parameters of the model theta. So you can think like a Gaussian mixture model or something like that. And a nice framing of expectation maximization is as a joint optimization over the parameters of the model and the distribution over these hidden variables. So then what EM is doing, EM alternates between finding the expectation over the hidden variable Z right? The optimal distribution being the conditional probability. And then maximizing theta using the expected complete log likelihood. Right, so EM just alternates between these two steps, fitting a distribution over the hidden variables, and then maximizing an expected complete log likelihood. So, so if this distribution of Z is too complex, we can substitute some simpler Q of Z, like a product, a mean field approximation. Just as one example, text models like latent Dirichlet allocation have a collection of topics, Z, that explain the appearance of words X in a document. So this is a latent variable model over documents. Each document has some collection of topics within it, and each word is assigned to one of those topics. So each word has a topic assignment Z. So if you reason in this system, typically you just reason about the Z's, and you want to optimize the parameters of the model. So then the two main methods of doing this are things like Gibbs sampling, where you use a conditional probability, or mean field. And so mean field has this nice form that we saw before. It's, we're fitting a product distribution over these latent variables Z, each of which depends only on the neighbors. So each Q of Z will depend on the factors of its involved neighbors. Okay, so this coordinate ascent gives us in fact, what you'll find is that if you do mean field in these models, often the mean field updates look quite a lot like the Gibbs sampling updates. Okay, so mean field gives us a lower bound. There's another technique that gives us upper or lower bounds called reweighted methods. And the most common, the standard one of this is called tree-reweighted belief propagation. So again, let's take this view where the log partition function is a convex function of our model theta. So we'd like to evaluate this log partition function at theta, but that's difficult. So instead, we're going to approximate it by picking a collection of easier models. So just like in mean field, where we picked some easier model and then did a linear expansion, here we'll pick two models that are easier in some sense, easy for us to calculate A of the partition function of. For example, tree-structured models. And we'll set them so that theta is some convex combination of those 2 points. So theta 1 and theta 2 will be easy distributions. So we're able to evaluate the log partition function on those two models. And then we'll use their convex combination as an upper bound of theta. Okay, so here's an example of this on, again, this pairwise factor graph. So we have one cycle, so 3 pairwise factors. We can create 2 easy to evaluate models, theta 1 and theta 2, by using tree-structured subcomponents of this model. So for example, I'll pick these 2 models. So theta 1 will be structured like this. Theta 2 will be structured like this. Right? And since they're tree-structured, they're easy to evaluate the log partition function just by doing variable elimination. Now what I want to do is pick their parameters, theta 1 and theta 2, such that some convex combination of theta 1 and theta 2 will equal my original model theta. Okay? So I'll just give them weights a half, and then I'll choose their parameters such that 1/2 times theta 1 plus 1/2 times theta 2 equals the original model theta. And since, so here I'll put theta 1, 3 in both of them, so that it's included twice with weight 1/2. Theta 1, 2, I have one term here, and it appears no times in this model, so I'll put 2 times that function, and that way when I multiply this by 1/2, I'll get theta 1, 2. And same thing for theta 2, 3, I'll put 2 times that function here. So now 1/2 times this plus 1/2 times this equals my original model, right? Theta 1, 2 plus 1/2 theta 1, 3 plus 1/2 theta 1, 3 plus theta 2, 3. Okay. So, so this ensures that my hard to evaluate model, the cycle, is this convex combination of these two easy to evaluate models. So then I can evaluate the log partition function of these two models very easily, and then their convex combination gives me an upper bound on the true log partition function. Okay. So just like with, this should remind you of the decomposition view from dual decomposition. We're taking a hard problem and we're breaking it up into smaller parts that are easier for us to evaluate. Right? So here we've decomposed this problem into 2 tree-structured models, each of which we're able to evaluate, and then we're bounding the solution to this joint model by a combination of these parts. And just like with dual decomposition, we can actually tighten this bound by, again, reparameterizing. So if we have this any variables that overlap between these two models, right? We can shift parameters from one to the other as long as they cancel, and that'll preserve that the convex combination of these two things is still equal to theta. And so by adjusting these parameters, I can tighten this bound. So in fact, this is just like the dual decomposition form. Also just like dual decomposition, so when we did a dual decomposition form, we had a dual of that, which was the linear programming. This tree-reweighted form also has a dual form, which is fairly nice. So I typically call this decomposed form the primal, and the other form the dual, even though in the LP form those are reversed. We can compute these bounds on the partition function either in this domain where we enumerate over these tree-structured forms. We assign weights to each tree, we assign some parameter vector to each tree, and then we ensure that the original model is the weighted combination of those simpler models. If we take the dual of this, what you find is that rather than having to enumerate trees, it takes a form like this, where you only need to keep track of what are called the edge appearance probabilities. So the edge appearance probabilities is the total weight that any tree that contains that edge has. So for instance, row 1, 3 here would be the weight of this tree, weight 1, plus the weight of this tree, weight 2. So, so rather than enumerating trees and their weights, you can actually express them all compactly in terms of just probabilities over each edge. And optimization in this dual form, just like the linear programming form, gives us, we can derive a message algorithm that looks quite a lot like BP. In fact, it looks exactly like BP, except it has an additional term, these weights. These edge appearance probabilities appear in the recursion in a weighted way. And so, in fact, these end up looking quite a lot like the counting numbers, where the contribution of this factor is being downweighted by the edge weight. So again, so these reweighted bounds can be used in learning and are often used for maximum likelihood learning for conditional random fields and things like that. So if you're doing maximum likelihood learning, your likelihood function, your log likelihood function, is just something that involves your model parameters and your observed data, and then the log partition function that normalizes the model. Right? So this is the data term, which you're trying to maximize with respect to the parameters, but then this log partition function makes sure that those parameters have total mass 1, so that as you try to assign more mass to the data, you're forced to reallocate it from other values. So if this is your log likelihood, but this log partition function is difficult to evaluate, you can substitute the log partition function with this variational form and use this reweighted upper bound, which means that you're optimizing a lower bound on the likelihood. So this is nice because you're at least ensuring that your data are at least as likely as your approximation is. And then if you use gradient descent on this, the derivative of the log likelihood will involve here a term that involves the data parameters, and here the derivative of your upper bound on the partition function, which will just be the beliefs computed via this message recursion. So the fact that the derivative of the log partition function are the marginal probabilities, the derivative of this upper bound are the beliefs of the approximation. You can also use this to get lower bounds. So exactly the same form, where I have two simple models, theta 1 and theta 2, a weighted combination of them. But if I choose the weights so that one weight is greater than 1 and the other one is negative, I get a lower bound. So here I have two models that are easy to evaluate. And then instead of choosing their convex combination in between, which would be an upper bound, I choose a point that's outside of the convex set. So now that's a lower bound on theta. And again, the same thing, right? We just choose our model parameters to be tree structured so that the log partition function is easy to evaluate. And now we have to choose our parameters such that this weighted combination, which I chose -1 times tree 1 and 2 times tree 2, so that now this positive and negative weight model will give us the original model theta. And again, if you follow this through, you find that now this weighted combination of partition functions is now a lower bound on the partition function. It turns out that this negative reweighted model is exactly like the positive reweighted model, the upper bound. And so in fact, you can, even though it's non-convex, you can optimize it using exactly the same message passing algorithm, but now with the weights chosen to be positive and negative. Unfortunately now, because of the negative values, it becomes non-convex. So when we're choosing an upper bound, our weights are between 0 and 1. And so that is a convex set. Now we're choosing weights that are greater than 1 and negative. And so that actually is a non-convex set. In fact, it's a disconnected set. So in this case, there's one region out here and one region out here. And also, because of the negative numbers, it turns out the objective function is also non-convex. So we have a lot of non-convexity problems with this lower bound. But actually, that's just like mean field. And in fact, mean field turns out to be a special case of this negative reweighted bound. To reconnect back to this approximate elimination form, the reweighted bound actually can be viewed as exactly the same approximate elimination that we saw in maximization. So in maximization, we used mini bucket. So we wanted to eliminate over x1 of a product of functions. But we decided that this collection of functions was too large. So instead, we split x1 into two parts, and we eliminated separately on one clique and another clique. In this case, you can do exactly the same thing. And the proper elimination technique is to eliminate one clique and the other using a weighted or powered elimination. So instead of summing over x1 in each part, we actually use a powered sum. So we sum with respect to weight 1 and weight 2, where those sum to 1. And what a weighted sum means is take its argument, raise it to the power 1 over weight. So this is like a powered sum. And then eliminate x1, and then raise that to the weight. So, so in fact, this approximate elimination with these two weights is an upper bound on this overall sum just via Holder's inequality. Or if you take the log of this, you can prove it with Jensen's inequality. So the sum of this entire thing is upper bounded by the individual sums using this weighted sum. And in fact, if you choose, just like the negative weights, if you can get a lower bound version if you choose one of the weights larger than 1 and the other weight negative. So one nice thing about this form is that it's extremely easy to do and to process. So you can just follow variable elimination, but as you proceed, eliminate your variables approximately. It's also extremely compact. So instead of having to enumerate all of these trees, their weights and parameters, I end up just expressing only the variable duplication that corresponds to this approximate elimination. So when I eliminate x1, I end up duplicating it, and I have a weight that tells me what the allocation of weight to those are when I eliminate x2, and so on. So, so this approximate elimination form has far fewer parameters than the full tree reweighted expansion. It also makes it very easy to use large cliques. So this tree form, it's pretty easy to enumerate over trees, but quite hard to enumerate over things like hypertrees, right? To enumerate over graphs that have larger clique structures. But using this approximate elimination form, you can just use an I-bound size parameter to define how complex of a function you're willing to take. In fact, actually, so just to sort of skip quickly, usually moving to larger cliques is much more effective than iteratively optimizing. So, so this is the gap between all possible trees and just the trees that are via this approximate elimination form. But if you move to using non-pairs, so it's triplets of variables, so I bound 2, your bound improves significantly. And as you increase the I bound, it improves quite a lot. So I just want to mention one last thing about this mixed inference that I mentioned at the beginning. This view of weighted elimination that lets us do upper and lower bounds actually has a lot of other power to it. So this weighted elimination operator that I defined, this powered sum, has the property that if the weight goes to 0, you end up with f to the infinity. It turns out to be the infinity norm of f, right? And so as your weight gets small, this powered sum approaches a maximization operator. And actually, if you have a negative weight and you do the same thing, it approaches a minimization operator. So you can think of this as like a zero temperature sum, basically. And the reason that's useful is now instead of looking at just the partition function using sums, we can actually define a weighted partition function that involves weights for every possible variable. And then we have a general form that can encompass both the partition function, combinatorial optimization, and also these mixed forms that involve things like decision making and policies. So what we can do is assign each variable its own weight. And for variables in this set that we want to maximize, we assign them weight 0. And for variables in the set we want to marginalize, we assign them weight 1. And so now this weighted partition function encompasses all of these three problems and lets us deal with them on equal footing and derive a variational form for this weighted partition function. And so what you find is you can get a variational form for mixed inference problems that actually generalizes the two forms that I gave. So it's still an expectation over theta, but now of a conditional entropy. So if we were maximizing over everything and summing over nothing, then this conditional entropy would just go away. And if we had no maximization variables and all of our sum variables were the whole system, this would just be H of A, so the joint entropy. So this, just as this inference problem generalizes sum and max, the variational form of it also generalizes the sum and max forms. And so you can actually derive message passing algorithms that look like belief propagation for these mixed systems. And they involve weights, so you end up just doing a weighted, reweighted message passing like tree-reweighted, except now instead of edges having weights, variables have weights as well. And so you end up with slightly more complex message passing forms. So in summary, I just want to emphasize the key perspectives behind variational inference. The two key ideas are that we can take a large problem and decompose it into smaller cliques, so reason only about smaller cliques, and then use reparameterization to shift parts of the model between those cliques and expose the parts of the answer that we're interested in. So in dual decomposition, we used reparameterization to expose the optima of the local factors. In tree-reweighted bounds on the partition function, we used reparameterization to expose the partition function of each convex part. The other key perspective is the convex nature of these problems. So the maximization problem is was a maximization over distributions or a linear program. The variational, the log partition function was also a convex function of theta. And so these have nice duality properties and variational forms where we can express them in terms of probability distributions, optimizations over distributions. So in terms of maximization, we had several perspectives on exactly the same optimization problem, where we could do variable elimination or a decomposition bound, and those were dual to a linear program or a variational relaxation. In summation, we use this convexity of the log partition function to give us bounds, either using mean field lower bounds or weighted upper or lower bounds. Or we could substitute an approximate entropy like the Bethe approximation and get message passing algorithms like Loopy BP. Using a weighted perspective gives us the ability to include not just max or sum individually, but any combination of max and sum. This gives us a general system in which we can use the same ideas of decomposition and Lagrangians to do reparameterization and get new message passing methods for solving them. Thanks.